Hello everyone. In today's session, we are going to learn about the K-maps, representation of Boolean expression using K-maps. The simplification of Boolean expressions using Boolean laws is time consuming as well as lengthier. We can use the Karnaugh maps, that is diagrammatic representation of the Boolean expression, and it is mainly used for simplifying the Boolean expressions. Using this technique, compared to the Boolean expression simplification using Boolean laws, it is faster and we can obtain the simplified expression very easily. So we also know the importance of simplification of the Boolean expression because it reduces the cost for hardware implementation. So let us now see how to represent the Boolean expressions in the K-map. So let's start with two variable K-map. We can see one example here. F of a comma b. So input variables are a and b here. It is a two variable function, and f of a comma b is equal to a bar b plus ab. Let us now see how to represent the Boolean expression in the K-map. So as we have two variables here, we can say that 2 power 2, that is 2 power 2. We can, in general, we can say that as 2 power n, where n is the number of input variables. So the number of input variables in this example is 2. Therefore, 2 power 2 will give you 4. So that means a K-map, two variable K-map will have 4 cells in it. So as shown in the diagram, we have 4 cells in the K-map. And now let us represent the input variables on the K-map. So the input variables are A and B. Let us consider A variable for the rows of the K-map and B variable for columns of the K-map. A variable can have value 0 and 1. So let us represent 0 and 1 for each of the row here. And B will have a value 0 or 1. Therefore, we represent values 0 and 1 for B under the columns. So we will define the values for variables A and B, and it is given here, and the same expression is represented in the tabular column. So let's consider the different combinations for A and B. So it is 0 0 0 1 1 0 and 1 1. As this is a minterm canonical form, we already seen that how to represent this expression in the truth table. So here, as this is a minterm canonical form, for each of the product term, we have to place logic 1. Therefore, the minterm A bar B will be high for the combination A equal to 0 and B equal to 1. Therefore, we place logic 1 here. So the next product term or minterm is AB, where A value is 1 and B value is 1. Therefore, we place logic 1 for the combination AB as 1 and 1. For the remaining combinations, the function will be 0. The function is true for the product terms A bar B and AB. Therefore, we place logic 1 here. So now this is what we have represented the truth table from the given expression. The same thing has to be represented in the K-map. Now let us see the cell numbers which is defined for the K-map here. So let us look into each row and column here. So the first combination, A is 0, B is 0. So you can see that A is 0 in this row and B is 0 in this column. So 0 and 0 will have a cell value as 0. Cell number 0. Similarly, the second combination, A is 0, B is 1. We can see that row 1 and column 2 will have cell number 1. See here, row 1 and column 2, that is 0 1. Therefore, this gives a cell value 1, cell number 1. Similarly, next combination is 1 0. Therefore, this will be cell number 2. Cell number 2. And the next one is cell number 3. Okay. So this is how we write the cell numbers in the K-map. Now let us represent the Boolean expression in the K-map. So for cell number 0, so let's write the cell number here. So this is 0 cell, 1, 2 and 3. So we have 0, 1, 2 and 3. So directly for the output values, whatever we have written in the column F, the same thing has to be represented in the K-map. So now let us write the values in the K-map. So for 0, 0 combination, 0th cell, we have value 0. Next for 0, 1 combination, we have logic 1. For 1, 0 combination, we have logic 0. Next for 1, 1 combination, we have logic 1. This is how you represent the Boolean expression in the Now let us see a 3 variable K-map and also how to represent a 3 variable function in the K-map. So we have a function f of a comma b comma c equal to a bar b bar c bar plus a b bar c bar plus a bar b c bar plus a b c bar plus a b c. So this is the given 3 variable function, and for this 3 variable function we have written a truth table, and as this is a minterm canonical form, for whatever the minterms are present in the given function, for the respective minterm we place a logic 1. So the minterms are shown in the truth table along with the different combinations of A, B, C, and also we have written the output column. So we see that A bar, B bar, C is a minterm given in the function, therefore we place logic 1. Similarly, A bar, B, C bar, we place logic 1, and A, B bar, C bar, we place logic 1. For combination A, B, C bar, we place logic 1, A, B, C, we place logic 1. For the remaining cells, we place logic 0 because these minterms are not present in the Boolean expression. As we know that 2 power n equal to the number of cells, it gives the number of cells. So here n is nothing but the total number of input variables. So the given number of input variables in the function is 3, therefore 2 power 3 gives you 8 cells. 2 power 3 gives you 8 cells. So we are representing 8 cells in the K-map. Now let us write the input and output variables in the K-map. So let's represent a variable for the rows of the K-map, and 2 more variables B and C are representing the columns of the K-map. So as we have 2 variables representing the column, we get 4 different combinations. So let's represent the value for variable A. So we have 0 and 1 here. So for BC, we write 0, 0, 0, 1, 1, 1, 1, 0. Now we know that the K-maps are the applications of gray code. So where in gray codes, whenever you compare any two numbers, any two binary combination, it will be valid only if there is a 1-bit variation in it. So whenever you consider the adjacent cells in the K-map, when you compare the adjacent cells in the K-map, it should have only 1-bit variation. So let's now see the first column and the second column. You can see there is 1-bit variation. So this is a right values which we have given for the columns of the K-map. So now let us go for checking these two. Suppose if you write 1, 0 here, there will be 2-bit variation in it, which is not valid. Therefore, we interchange the columns or interchange the values in the K-map representation as shown here. Therefore, we always write 1, 1 in the third column and 1, 0 in the fourth column for 3 variable K-map. So here we see that when we compare these two adjacent cells, we have only 1-bit variation, which is valid. And when we compare the last two, that is 1, 1 and 1, 0, we again have 1-bit variation. And also we know that the K-maps can be folded in order to group the cells. So the last column and the first column will be adjacent to each other. When we compare these two adjacent cells, that is 0, 0 and 1, 0, we again get a 1-bit variation. Therefore, the values whatever we have written for the rows and columns are valid. So therefore, these two has to be interchanged. Now let us represent a 3 variable function given here in the K-map. So for the combination that is given in the Boolean function, we will place logic 1. So before we place logic 1s in the K-map, we just write the cell numbers. We will define the cell numbers. So we have a cell number 0 here for combination 0, 0, 0. we can write the cell numbers by considering the binary values of A, B, C. So 0, 0, 0 gives you 0. Next 0, 0, 1 gives you cell number 1. Next cell is 2. 2 is 0, 1, 0. So we find 0, 1, 0 here. So we write cell number 2 here. So we shall write that. So cell number 1 is here. Cell number 1 is here. Cell number 2 is here. Then cell number 3 is 0, 1, 1. Therefore, we write cell number 3 here. Cell number 4 is 1, 0, 0. 4 is here. 5, 6, 7 is 1, 1, 1. Therefore, we write 7 here. Now, let us place the values into the K-map for the given Boolean function. So, cell number 0 is having logic 1. We place logic 1. Next, it is 0. Next is 2. Cell number 2 is having logic 1. We can see that 2 is 0, 1, 0. Therefore, it is logic 1. We write logic 1 in the cell number 2. Next combination, we have 0. For the next combination, that is 4, we have logic 1. For 5, we have 0. For 6, we have logic 1. For 7, we have logic 1. So this is the representation of K-map for 3-variable Boolean function as shown here. In the next example, we will see how to represent the given expression in a K-map. So the given expression here is of 3-variable function. So the input variables are A, B, C, and it is a min-term canonical form represented in a decimal notation. So for given min-term canonical form, you need to place logic 1s for the decimal numbers given there. So let us place logic 1 for the combinations 1, 3, 4, 5, 7. So let's place 1, 3, 4, 5 and 7. For these combinations we are placing logic 1. For the remaining combinations we place logic 0. The same Boolean expression will now be represented in the K-map. So we already have seen how to represent a 3-variable K-map. So let's directly go for representing the values in the K-map. So we have A, B, C. A is considered for rows of the K-map and B, C is considered for the columns of the K-map. So A can have value 0 and 1. B, C can have 0, 0, 0, 1, 1, 1 and 1, 0. Now we know that the cell numbers of the K-map will vary from 0 to 7. So directly we can place by looking at the truth table, you can place into the K-map. So we have for cell number 0, we have value 0. For cell number 1, we have logic 1. Cell number 2 is 0. Cell number 3 is 1. Cell number 4 is 1. Cell number 5 is 1. Cell number 6 is 0. Cell number 7 is 1. So this is the K-map representation for the given Boolean expression. Next we will see a 4-variable K-map. So 4-variable K-map, the given expression here is f of wx yz equal to summation m 0, 1, 5, 6, 11, 12, 14. So for 4-variable K-map, let us find out the total number of cells in the K-map. So 2 power 4 gives you 16 cells in the K-map. So we have 16 cells represented in the K-map. The variables here given are w, x, y, z. So we are representing 4 rows and 4 columns to obtain 16 cells in the K-map. So let us represent the variables w, x and y, z. So for w, x, we can for 2 variables w, x, we have 4 different combinations. So let us represent those combinations for every row and every column. So wx can have 0, 0, 0, 1 and next we are representing 1, 1 and 1, 0. We are interchanging the rows here because it has to be a valid gray code application. So therefore we are interchanging the rows here. The same thing applies for the column as well. So yz is 0, 0, 0, 1, 1, 1 and 1, 0. So defining the cell numbers of the K-map, we can look into the combinations of w, x, y, z, that is 4 variables. We have 16 different combinations starting with 0, 0, 0 to 1 1 1 1. So zeroth cell is represented by 0 0 0 0. We can look into the combination here. Wx is 0 0 here, yz is 0 0 in this column. So with this row and this column we have cell number 0. Similarly for cell number 1 is represented by 0 0 0 1. Therefore Wx is 0 0 in this row, that is first row, and in the second column you can find yz as 0 1. So this particular cell becomes cell number 1. So let's represent the cell numbers for each of the cell in the K-map. So this will be 0 1. 2 goes to the last column because the value for 2 is 0 0 1 0. Therefore this becomes 2 3, and 4 is 0 1 0 0, then 5 6 7, 8 is 1 0 0 0. So we can find wxyz as 1 0 0 0 at the last row and the first column. Therefore this becomes cell number 8 9 10 11. This becomes 12 13, cell number 14, and cell number 15. Cell number 15 is 1 1 1 1. So we can find in third row and third column. Therefore we write cell number 15 here. Now we have just written the cell numbers in the K-map for the 4 variable K-map. Now let us plot the K-map for the given Boolean expression. As the given Boolean expression is a min-term canonical form, we are going to write logic 1 at the output column F for the given decimal number. So it is high for 0, 1, 5, 6, 11, 12 and 14. So let us place the logic 1 value at the output column F for the given decimal number. So this is 1, 1, combination 5 is 1, 6 is 1, then 11 is 1, 11 is 1, 12 is 1, 14 is 1. For the remaining combinations, you are going to place logic zeros. So now, after placing the logic 1 and logic 0 values in the output column according to the Boolean function, let us plot the same thing in the K-map. So we know that we are placing logic 1 for the min-term canonical form. Therefore, we will place cell number 0 with logic 1, then logic 1, 0, 0. Just look into the truth table here. Already we have placed according to the given Boolean function. Looking at the truth table, you can directly place the logic 1 values. Else, from the expression itself, you can directly place the logic 1 values in the K-map. So for cell number 4, it is 0, 5, 1, 6, 1, 7 is 0, 8 is 0, 9, 0, 10, 0, 11 is 1, 12 is 1, 13 0, 14 1, 15 0. This is how you place or plot the K-map for the given expression. Now let us see how to plot the K-map for max term canonical form. So we have already seen how to represent the K-map for min-term canonical form. Let us now represent for max term canonical form. So the given number of input variables are 3 input variables for the function. So 2 power 3 gives you 8 cells in the K-map. So we have represents 8 cells in the K-map. Let us consider the input variables onto the K-map. So it is x, y and z. So x will have 0, 1, yz will have 0, 0, 0, 1, 1, 1 and 1, 0. So for max term canonical form, for the respective max term, we place logic zeros in the output column for the combinations 0, 3, 5, 7. So let us place logic 0, that is for combination 0 and 3 and 5 and 7. For the remaining combinations, you need to place logic 1. The same thing has to be represented in the K-map for the cell numbers 0, 3, 5 and 7. So we already know how to identify the cell numbers or write the cell numbers of the K-map. So this is 0th cell, 1, 2 and 3. This is 4, 5, 6 and 7. Okay, let us now write the values into the cell. So this will be 0, 1, 1, 0, 1, 0, 1, 0. Okay, so this is the representation of max term canonical form in the K-map. In this example, we will plot the K-map for a given max term canonical form. So we know that the input variables here are A, B, C, D. So we have 4 input variables. Therefore, we consider a 16 cells in the K-map. That is 2 power 4 gives you 16 cells in the K-map. The easiest way for plotting the K-map for such expressions is just represent each max term with its binary equivalent, so that for plotting in the K-map it will be very easy. And we know that the max term canonical form, for each of the max term you need to place logic 0 into the cell. So let's plot the K-map. So the input variables are A, B, C, D. Let us write the values for each of the row and column for the respective variables A, B, C, D. So it is 0, 0, 0, 1, 1, 1, 1, 0. Similarly for the columns it is 0, 0, 0, 1, 1, 1 and 1, 0. Now we know that for representing each the max term representation, 1 is considered as complementary variable and 0 is considered as uncomplementary variable. So let me write the values for each of the max term here. So A will be considered as 0, B will be considered as 1, B bar will be considered as 1. So C bar is 1, D is 0. Similarly here we have 0, 0, 1, 1. Similarly here we have 1, 0, 1, 0. Next we have 1, 1, 1, 1. So from this you can easily identify the decimal number from the binary representation and directly place logic zeros in the respective cell number in the K-map. So first cell number what we have here is 6, cell number 6 for the first max term, that is 0, 1, 1, 0, and the second max term is cell number 3, and the third max term will give you 10, cell number 10, and the last one, the last max term will give you cell number 15. For these cell numbers you need to place logic zeros because these are max term. In the remaining cells you will place logic 1. So let's now write the cell numbers here. So it is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Cell number 12, 13, 14, 15. Okay. For the cell numbers, now we have already seen for cell numbers 6, 3, 10 and 15, we are going to place logic zeros. So directly place logic zeros for the cell numbers. So 0, 0, 0, 0. For the remaining cells, you will place logic 1. So this will be the representation of K-map for the given max term canonical form.